Hey, thanks for watching. This is part one in a two-part series. We did a class at the Kalos offices with some of our techs and some of the apprentices, installers, on low voltage electrical basics, focusing on finding shorts and opens in various circuits. But in this first video, it's really just a lecture from me, kind of prepping the conversation, attempting to get some of the basic language right in order to make our time diagnosing hands-on a little bit more productive. Hope you enjoy. All right, so today we're going to talk about electrical diagnosis, and specifically we're going to focus on low voltage electrical diagnosis because that's the area that most technicians say they struggle with. If you poll any group of kind of junior to mid-career technicians, low voltage diagnosis and electrical diagnosis in general are the things that people struggle with the most, along with diagrams, schematics, those sorts of things. I actually want to start with a comment that I got on YouTube the other day. I think it was on YouTube, maybe it was on the website, but somebody said that they wanted more training on how to diagnose circuit boards. They wanted to know more about circuit boards. And that's a good place to start because it represents a black box that people don't understand. And so what they want somebody like me to do is to explain how circuit boards work generally. But there's a problem with that. What's the problem with that?
Each circuit board is designed to do something different.
Yeah, each circuit board is designed to do something different. So in order to teach somebody about circuit boards, you would be teaching them about electronics, right? That would be the only thing that you could talk about that would be general enough that would have any meaning. But do we fix or repair circuit boards in the field?
No.
Answer is no, we don't. So I can teach people in the field how to repair and understand circuit boards, and that would waste a lot of their time. Now, it's not to say that that's not a valuable profession, but that's not the profession that we're in. So what do we really need to know about circuit boards? We need to know inputs and outputs, right? And that's what everyone says, and somebody said that, I'm frustrated, I want more than just inputs and outputs. Well, that's what you have to understand, and then you have to understand sequence of operation. So in order to understand a circuit board, you have to understand what is that circuit board designed to do. If you don't understand what it's designed to do, if you don't start there, then everything else you know about, resistors and capacitors and everything else is pointless. It doesn't mean anything. Knowing that doesn't help you fix air conditioners. So I want to start there quickly and just review specifically what we're talking about is residential air conditioning and heat pumps. We focus mostly on heat pumps. That's where we spend most of our time, and that works anyway because the low voltage electrical tends to be a little bit more complicated on them. So you have to understand the basic circuits within those systems. Now, that's not what this video is about. It's not what this class is about specifically, but you have to start by understanding what R is, what C is, what W is, what Y is, what G is. And those are just terminal designations. People will often say, what color wire should go to it. Well, electricity is colorblind. Electricity does not care what color the wire is, but it does matter that the start of this circuit being on this conductor on this end ends up on the right place on the other end. And so a lot of what we're doing is making sure that we're connecting things in the right places so they go to the right spots. And in terms of an installer's responsibility, in terms of a service technician's responsibility, so much of what we do comes down to that. I think ductless systems, they talk about how, I'm making this up, but I think I heard this at one point, 70% of the problems with ductless systems have to do with the electrical wiring being done incorrectly. Crossing wires or not making good connections. All the time, those are the sorts of problems that we run into. And a lot of the issues that we run into in the field, specifically with low voltage diagnosis, start with really, really obvious and simple practices that we have to get right. But let's start with a couple things, sequence of operation, just some things that you need to know about a piece of equipment. So let's talk about the difference between a straight cool system and a heat pump system, juxtaposition. So start with Y. Y, what we would commonly call the yellow circuit, even though it doesn't matter what color the wire is, but it's the Y circuit. What is the Y circuit? Somebody in the audience. It's okay. You don't have to have a mic.
Contactor. I have a mic.
Okay, so Eli said contactor. What else would a lot of people say the Y circuit is? Compressor. They would say it's the compressor. Cooling. What else? They would say it's cooling, right? And so is it all of those things? Yes. Is it more than those things? Could be. Right? So you have to know what we're saying when we say Y. We could have a two-stage system. They could have Y1 and Y2. Let's use that as an example quickly. Y1 and Y2. What do you need in order for a two-stage residential piece of equipment to run at full capacity? in terms of your terminal designations? What do you need to energize?
Y1 and Y2.
Y1 and Y2, right? So a lot of people, if you don't know that, you would think, well, you'd have Y1, that's stage 1, and then you go to Y2, that's stage 2, right? But it's actually Y1 plus Y2 equals your high stage, your full capacity operation, right? So it's things like that. You got to start with knowing that about your equipment. What are each of these terminal designations for? When should they be activated? That sort of thing. When we talked about cooling versus compressor versus contactor, all of those are true in one sense, but where's the problem with saying that Y is the cooling call? What's the problem with that?
Heat pump application.
In a heat pump, it's your contactor, right? It's what specifically energizes the electromagnet on your contactor. Let's grab a contactor here quickly. So what is Y really? Well, Y energizes our contactor coil, which is an electromagnet, which then pulls in our contacts, which then allows our compressor and generally our condenser fan to run. So it's a much more complicated story than just saying it's cooling. Now, if this were a straight cool unit, typical gas furnace or a system that just has electric heat strips, that would be all that cooling would be. You just energize that and your outdoor unit runs. Depending on how the system's set up, you may also need a G call in order to run your blower, but that's basically it. But on a heat pump, why isn't this cooling on a heat pump by itself?
Because you have a reversing valve.
Because you have a reversing valve. Tanner answered, yeah. You have a reversing valve. And the reversing valve does what?
Switches between cooling and heating.
Yes, the reversing valve switches between cooling and heating. So the compressor contactor stays pulled in either way, whether you're in cooling or in heating. And then in order to run in cool mode, you energize O. We call it orange, but again, that's just a color, doesn't matter, but that's the O terminal. We energize O on most heat pumps we work on in the cooling mode, and that's what designates cooling because that reversing valve switches into the cooling position. So there's a lot of things like this. And again, like I said, we're not going to go through every single circuit here, but if you don't understand what each circuit does specifically on the piece of equipment you're working on, then start there. Start by memorizing that. I know we don't like to memorize anymore, but for newer technicians, especially if you're thrown into the deep end, you don't have a lot of theory behind you, you don't have a lot of the basics, you haven't read the rack manual, you haven't been to school, which is a lot of technicians nowadays. Memorize 2 sets of things. Memorize your standard 4 components of the refrigeration cycle. Compressor, condenser, metering device, evaporator, your standard 3 lines, discharge line, liquid line, suction line, and then memorize all of your standard circuits on the low voltage side. Because those are things that you're going to interact with all the time. Those are very easy, but literally just memorize them. Memorize what they do on a heat pump, memorize what they do on a straight cool. Once you know that, it's going to be a lot easier to understand what we're doing. Be a lot easier to teach you, exactly. It's going to be hard to teach if you don't have some of these basics memorized. And honestly, when I went to school, one of the best things my instructor, Ron Carey, did was he sent me to the whiteboard and he said, all right, we're going to draw a compressor, condenser, metering device, evaporator, and you're going to do that over and over again. And you're going to mark them, you're going to mark the lines, you're going to write what's in each line and what each component does. I'm going to erase it, you're going to do it again. And I did that for the first couple days until I had it memorized. So that's on the refrigeration side. On the electrical circuit side, it's just what each one of those terminal designations does. And as you go through and you memorize straight cool, that's easy. Then go into heat pump, then go into multi-stage heat pump, then go into systems that have accessories like dehumidification. So let's go over some of the standard diagnoses that you're going to make on low voltage and knowing the difference. Because in terms of language, using the right language to designate what you're doing or what you're finding or what you're looking for in the system, if you don't get this straight, it's going to be really difficult for you to learn this. So let's start with a couple terms. The first one is short, and we're going to define a short quickly. So let's do that. Eric, what is a short?
It would be when your circuit's not going through an intended path.
Your circuit's not going through an intended path?
Touching another path that it shouldn't be. Either another wire or ground.
Another path that it shouldn't be, exactly. So it's taking an unintended path. So there is an unintended path that exists that shouldn't be there. So the way that I've always said this, and I can't think of a better way, something's happening that shouldn't be happening, right? You have a path that shouldn't be there. It's taking a shortcut, right? As we all know, we're not supposed to take shortcuts in doing our work, right? So that's what the electricity is doing, is it's taking a shortcut. It's taking a path that it's not supposed to take. But that leads to the question, what path is it supposed to take? Right? So you got to know that. What path is it supposed to take? So again, let's think about the Y circuit. Super simple. Y circuit goes to one side of the contactor. That's where it ends up. It may go through a wire nut, it may go through a terminal block, may end up on a circuit board, but eventually it's going to end up on one side here, right? But where does the other side go? So if the Y circuit is ending up on one side of our electromagnetic coil, what's going on the other side? Common, right? What does common mean? This is a really good one. This is a really important one. Someone actually asked this today. What is common? What is it?
The other side of the circuit to complete it.
The other side of the circuit to complete it? Okay, that's a good answer. I like that. Let's keep going with that. What is common?
Common is a common point in a specific circuit.
A common point in a specific circuit. Okay. All right, you reuse the same word. I think that's what we call cyclical thinking. That's fine. Go ahead.
Common is one side of the transformer, and every other wire is the other side.
Okay, one side of the transformer and every other wire is the other side. But let's think about it more generally, because common isn't just on transformers, right? We say common all the time. So I started with these two because these are the two of the most misunderstood phrases electrically that get used. Okay, so let's start. We're going to go back to short, and then we're going to hit common again. Short is what happens when your grandma says the TV's not working, right? My TV's acting all weird. Probably has a short. Must have a short. That cord has a short in it. And what does short come to mean in modern day life? Because we've all said it. Like, before you started doing air conditioning work, you've said the word short before. You've heard the word short before, right? It's Brendan, is that right? Brendan's new, so forgive me. But Brendan, you've heard the term short before you started working on air conditioning, right?
Yeah.
And how would you use it? How would you hear it used?
Same thing you said, grandma with TV.
Yeah, something's not working. If your car's acting up, right? Something's happening with the car. It's it's stalling out on you. They're gonna say, "Oh, it must have a short. I think it has a short." But what people mean by a short is some random electrical problem that I don't understand. That's what short has come to mean. But a short is a very specific type of electrical problem. And so when we say short, we need to know what we mean when we say short. Specifically with low voltage electrical problems, so let's back it back to that. What's generally going to happen when we have a short? Blown fuse. Blown fuse or tripped breaker on the transformer. Sometimes the transformers will have a low voltage circuit breaker on the transformer, and that's going to be tripped. It's going to be overloaded. So why does a fuse blow? Why does a fuse blow?
Voltage isn't going to the intended
Voltage isn't going to the intended point. Okay, there's some truth there. But why does it? But what's the number listed on a fuse? You've all seen a fuse before, right? What is that? You've all seen a fuse before, and it has a number on it. What is that? What does that number mean? Amps. It is. Well, there's another word that we don't know what it means. That's a cool one. So let's address that quickly. So what is amps?
Electrical flow.
Electrical flow. Okay, yeah. It's doing work, right? But what is it really? What makes it different than some other things that we measure like watts and volts? So we give a number to amps. So 0.001 amp is electrical flow and 100 amps is electrical flow. What makes them different from each other? What makes 100 amps different?
One's a lot more.
Oh, one's a lot more. Right. Okay, this isn't a trick, but it's more. But it's a more of what?
More current?
It's more current. It's more electrons, right? More electrons are moving. That's all. Right? Voltage is the pressure. How much pressure is there? And amperage is the amount of current, right? So when you have a 3 amp fuse, or let's say a 5 amp fuse, that's the most common. You have a 5 amp fuse, and that bad boy blows. It blows on you, right? What caused that? Too much amperage, too much current, too much flow. Above what number? If it says 5 on it, what does that mean? It was above 5, right? And in fact, if you were to run, say, 6 amps through a fuse, do you think it would blow right away? It would not. It would sit there for a while, and then eventually it would probably blow. It might not even blow, but eventually it probably would blow. But if you tried to run 100 amps through it, what would happen? Pop right away. And what happens if you take a low voltage wire, like your Y wire or your red wire, something that's energized, an energized conductor, and you touch it to ground? What happens? Pop, right? Instantaneously, fuse blows, right? If you've done it sometime, you see, you get a nice little arc, fuse blows. Why does it blow quickly? Based on what we just said. I'm leading you down a path here. Why does it blow quickly? Way too much current, right? There's too many electrons moving. And why are there too many electrons moving?
Because you created a path with no resistance.
Because you created a path with no resistance, with very little resistance, okay? So there's a couple other terms we got to know. We got to know the term load. So the electromagnet on your contactor, the part that makes it pull in, that's a load. It has resistance. So in order for a circuit not to blow a fuse, in order for a circuit not to draw too much current, it has to go through its intended path. And its intended path is through a load. It's also through a switch. It's also through certain wires and circuits. But it's through a load. Make sense? My nose all of a sudden is getting really itchy.
Take care of that.
Hmm?
You take care of that.
I will. I'm going to. I'm going to just... Yeah, there we go. Now I feel better. Okay. Maybe it's this super toxic contactor that's right in front of my face. All right. So when we have a blown fuse on a system, when you walk up to a system, this is the installer's most dreaded moment. We have a couple installers here, so I'm going to make fun of you. Oh, it's not your most dreaded moment
I
anymore?
like service. It's never.
Really? Okay, good. Well, good for you. Most installers, their most dreaded moment is when you fire up the unit and it doesn't run, and you open it up and it's got a blown fuse. Right? All right?
Right.
It's pretty dreaded. Even a lot of service techs don't like that very much, right? But so when you see that blown fuse, what do you know? Don't guess. What do you know for a fact? Sam?
At some point, some high current went through that fuse.
Too much current through the fuse, right? That's what you know. There's too much current. And what is the most likely cause of too much current?
A short.
A short, right? And a short that bypassed a load. So it went straight from one side of the power supply to another. If we think of like a really basic circuit here, if we think of like the most basic circuit, we've got a battery. And through that battery, we have a switch. And then it goes to, we're just going to draw a really simple light bulb here. And by really simple, I mean very poorly drawn light bulb. So this currently is drawn as an open circuit because the switch is open, but let's go ahead and draw the switch closed. So now we have a path. We have a completed circuit. And this circuit is not shorted as it is currently drawn because the electrons have to move through the light bulb. And so it'll light up the light bulb, right? That light bulb adds what to the circuit?
Resistance.
It adds resistance to the circuit. The resistance is what keeps the current down. It pushes back against the current, and it keeps it from being too much. We have some great videos from Ty Brannaman. He's done some really great classes on just kind of describing that, pushing people around in office chairs and that sort of thing. You get the idea that if you don't have a force pushing back against those electrons moving, then you get too much electrons moving, too much current, and that leads to a blown fuse, right? So that's what you know for sure when you got a blown fuse. Something caused the current to be too high. And most likely, it's some version of this. So this guy right here is a short. You got a path that's not supposed to be there. It's bypassing the resistance, and it's making the fuse blow, right? Too much current. So that's what a short is. It's very specific. Now, there's a different kind of short. And you need to know this because as we do these classes, and we're going to do a lot of them on these trainers, this is a hands-on class, and we're going to get there pretty quick. As we work on these trainers, there's a different kind of short that doesn't involve a blown fuse. And some people will argue that it's not a short, but I still think it is. And what is that different kind of short? If you have two wires that are rubbed out, connecting each other, touching where they're not supposed to be, there's a lot of innuendo in there, but we're gonna just pass by it. We're just gonna ignore it. We're gonna pretend like it didn't happen. but they are on the hot side of the circuit. They are on what we call the switch leg. So most of what we're working on in terms of our circuits are in between our switch and our load. So that would be things like Y, that would be things like O, that would be things like G, that would be things like W. Those are all standard circuits that are in between the switch, which is what, by the way? What is the primary switch in a typical air conditioner? Thermostat is the switch, right? It's the traffic cop. It's the one saying who goes where, what turns on, what turns off, in the right order. But most of these circuits are in between our switch and our load. Our load is whatever they're turning on and off, your reversing valve, your contactor, your blower relay, your heat relay, your gas furnace, whatever it is, right? They're turning something on and off. But what happens if those two touch each other? That's what we would call a switch leg short. That's a term I completely made up, but it's the best one I can come up with. Where there's an unintended path, and the result is not a blown fuse because you don't have too much current. It's not bypassing the load like this one is. It's just bypassing the switches. The switches are getting mixed up, the circuits that are past the switches. And that's resulting in things running when they shouldn't be running, mostly. So that would result in things like if your white wire, for example, on a heat pump crosses with your O wire, your orange wire, what would happen? I'm just going to ask it as a question. What would happen if you mix together white and orange and those two touch? Heat strips would come on in cooling. Interesting. But what else would happen?
Cooling would come on whenever the heat strips
with the heat strips, right? Because those two circuits would be completely crossed. So heat strips would come on with cooling. Cooling would come on with the heat strips, meaning reversing valve would be energized in this case because it's a heat pump. Those two circuits are crossed. So that's a type of a short. And often, like when we talk about things going haywire in our car or whatever, that's a lot of times what's happening. You have circuits that are mixing that shouldn't be mixing. They're connecting that shouldn't be connecting. And it's not necessarily always bypassing the load, bypassing the resistance, which results in a blown fuse. Okay? So that's important to know. We got some clarity on what a short is, unintended path. All right. What is common? Common basically just means a place where you connect things together. That's really what it means. Because think about a common on a capacitor, the C terminal on a capacitor. That has nothing to do with the common side on the compressor, the C terminal on the compressor. They're on opposite sides of the circuit, but they're both called common. But in a capacitor, it's the common point between two capacitors. So it's a point where they're connected together. On your compressor, for example, common, the common terminal on your compressor, what is that?
It's a common point between the two windings.
Common point between the two windings, exactly. You don't have a common winding. You have a common point between two windings. Run and start, connect together, common. On a low voltage circuit, what is common? Jessica. Low voltage circuit, what is common? You know.
It's the other side.
It's the other side of the 24, but where does it end at? Where is the ultimate point where common connects?
Ground.
Kind of. It can. But it's actually the transformer. It's the other side from hot on the secondary side of the transformer. Right? So that's where the 24 volts comes from. One side is common, one side is hot. Now, often common is grounded. They dedicate common to ground in order to make diagnosis easier and everything a heck of a lot less confusing. And we're not going to talk about that right now, what happens if you don't ground it. But that's what common is. Common just means a point where things connect together. And if you think that common is a universal term, then you're going to connect things where they shouldn't go. It only takes connecting your common wire on your low voltage side to the C terminal on the capacitor once to realize that it makes fire and stuff. Okay, cool. So the next term that we need to all get straight and is really important to distinguish from short is an open. What is an open?
A break in a path.
Incomplete path, break in a path. It could be designed or undesigned. So a switch opens and closes a circuit. So open is the juxtaposition, the opposite of closed. Right? Now the problem is that people get confused with this, and you know, like, you can make fun of it because we've always, those of us who've done this a long time have always known this. But what happens when you open a faucet?
You get water.
You get water, you get flow. What happens when you open a switch?
No flow.
No flow, right? So it's the opposite. What happens when you open a door? You can walk through it. What happens when you close a door? You can't. Well, it's the opposite. So the best way to think of open and close is opening and closing a drawbridge. That's the best way I've come up with. When the drawbridge is open, the cars can't pass across. Now the boats can, so that makes it kind of ruins even that one. I've heard that.
Cars can if you're brave enough.
Yeah, that's true.
Watch more
It's true.
movies.
Just Evil Knievel, that bad boy. Just leaper. But open means a break in the path. That could be designed like that, but it could also be if I take this wire going to my float switch right now and I cut it. That's an open, right? If the water rises in the float switch and it trips the float, it rises the float, what does that do to the circuit?
Opens
It
it.
opens the circuit, right? So what happens when a circuit is open? What happens to the system?
Electricity stops flowing to the component.
Electricity stops flowing to whatever circuit we're talking about. So if there's an open in the Y circuit, back to the old ubiquitous Y circuit, what's going to happen? Compressor contactor is not going to pull in. Compressor contactor doesn't pull in, that means that your condenser fan in your compressor is not running, right? So pretty simple. If your float switch opens, it's going to generally, we wire it to break R, which is our main 24-volt power, so everything's going to shut off, except maybe the blower time delay. That's one that always confuses people, right? You trip it and then it just keeps running for a while. What's going on? It's magic. Anyway, so that's what an open is. So here's what I don't want you to do as we're going through this, because we're about to get hands-on here, about to get handsy on these things. I don't want you to confuse open and short. So if I ask you what's going on with this system, don't automatically say one or the other. Think through. If it's a short, then something's going to be happening that shouldn't be happening. Either a fuse blowing or circuits cross where one thing's running when it shouldn't be running. It's not time. It's not in the right order. Right? Those would be a short. Whereas an open would be nothing's happening on a certain circuit or with the whole system. Right? Make sense? All right, cool. Any questions about what we've covered here so far? So you'll notice a couple things we didn't cover because this is only a 2-hour class, actually a little less than 2 hours because some of you are not naming names. But we're not covering schematics. We're not covering, identifying components or any of those. Those are for different classes. But today's class is specifically diagnosis, but I wanted to get some of these terms straight first. Let's talk quickly about the meter for any of you who are new to the meter. The first thing I always want to see you do before you use a meter, this is just a really good habit to get in the habit of doing, is take your meter and put it on where? Where should we put it first before you use it? Ohm scale. Because what is a meter doing when you put it in ohm scale?
Sending out voltage on the leads.
Sending out current, right? So there's a potential across these two leads. That means voltage between them. It's not much. It's not going to shock you, right? But there is some voltage at the tips of these leads. And what is it looking for?
Path.
Looking for a path, right? Now, don't pay too much attention to that ringer because different meters have different ohm levels at which the ringer will go on and off. So look at what it's actually telling you. If I put them together, what's my readout here?
0.
0, very near 0, right? That means that my leads are intact. Because I wouldn't want to start trying to test and be like, I'm not getting anything, right? Also, be really careful with the term no. I'm getting no ohms, or I don't have any ohms. I don't have any, I'm not getting any. Because that could mean that I have a perfect path, right? Because could you say right now that I have no ohms? I could say I don't have any ohms, right? And that means that I have a near perfect path, there's almost no resistance. But I could also say, see right now, what's the screen show? Just a series of dashes. So I could say right now, I've got no ohms. I'm not getting any ohms. So what is the right term? Infinite ohms? 0 ohms or near 0 ohms. Right? So 0 in this case means no resistance or almost no resistance. And this, when they're not connecting and there is no path, means infinite. Right? Open path. So that's another way to think of this. Closed, open. But why am I doing this again before I start testing anything else?
Make sure your leads are
Make sure my meter and my leads, right? Now, is that the best way to check? No, the best way to check would be to put it on the volt scale and then actually measure on a known power supply. So actually take it and plug it in to an outlet and see what am I getting. So now we have 120 volts. So that's a better way because now I'm actually checking to see that my if I'm measuring voltage, that my voltmeter is actually working. Cool? So I want you to do that first. If you're working on any live circuits, you need to be wearing safety glasses. Okay? So get those. I know we got extras. Mario can hook you up with some if you don't have any. So definitely be doing that.
Thanks for watching our video. If you enjoyed it and got something out of it, if you wouldn't mind hitting the thumbs up button to like the video, subscribe to the channel, and click the notifications bell to be notified when new videos come out. HVAC School is far more than a YouTube channel. You can find out more by going to hvacrschool.com, which is our website and hub for all of our content, including tech tips, videos, podcasts, and so much more. You can also subscribe to the podcast on any podcast app of your choosing. You can also join our Facebook group if you want to weigh in on the conversation yourself. Thanks again for watching.